Okay, hi, we're doing Nature of Sound, page 36 on your book. We've had an interesting morning so far. Okay, so we're back again. The old riddle, if a tree falls in a forest, no one hears it, does the tree make a sound? Yeah, it does. Because in order, when that tree falls, and what it's talking about, when that tree does fall, it is causing vibrations and everything, so it is making a sound. Now, just because someone maybe not is in the forest and they don't actually hear it, doesn't mean it didn't actually make a sound though, okay? Because when a tree crashes down, the energy with which it strikes the ground causes a disturbance. Particles in the ground and the air begins to vibrate or move back and forth. The vibration creates a sound wave as the energy travels through the two mediums, okay? Now, here's the thing. Sound is disturbance that travels through a medium as a longitudinal wave, okay? So making a sound wave begins with a vibration, okay? And if you look at the picture up top there, you see that metal gong. When that gong is struck, it vibrates rapidly, and the vibrations disturbs the nearby air particles. And each time the gong moves to the right, it pushes air particles together, creating a compression. When it moves to the left, the air particles bounce back and spread out, creating a rarefaction, okay? And so these compressions and rarefactions travel through the air as a longitudinal wave, okay? Remember the spring, we talked about the spring, compress, spread out, compress, spread out, going in pretty basically across. That's a longitudinal, okay? Sound travels like other mechanical waves. Sound waves can carry energy through a medium without moving the particles of the medium alone, okay? Each particle of the medium vibrates as the disturbance passes. When the disturbance reaches your ear, you hear sound. So what happens if I holler at Morgan over there, she hears me immediately, but what's happening is the vibration of my voice breaking the air all the way across, that's how she hears me, okay? If someone drops something in the hallway on the far end down there, and you're standing halfway down the hall, you think you're going to hear it before I hear it in here?
Yeah.
Yeah, you would. It would be real close. It's not like you're going to hear it and 15 seconds later I hear it.
Yeah.
It's going to be boom, boom. But you would actually hear it first because the vibrations are going to reach your ear first. Okay? Here you go. A common medium for sound is air. But sound can travel through solids and liquids too. For example, when you knock on a solid wooden door, the particles in the wood vibrates. And that vibration makes the sound waves that travel through the door. And when the wave reaches the other side of the door, then they make sound waves in the air on this side. So if somebody knocks on that door, it causes a vibration of the wood, and that vibration works its way through the wood and all the way through. And when it reaches this side, it starts moving the air. It's disturbing the air. And that is why we can hear the knock. Okay? Interaction of sound waves. Sound waves interact with surfaces that contact with each other. Sound waves reflect off objects, diffract through narrow openings and around barriers, and interfere with each other. The other day when we did the water waves in the tub,
Oh, yeah.
and we disturbed it and it went up and we had the barriers in and then it spread out around them. Light and sound does the same thing, okay? That's why these lights right here, it just doesn't light up just an area straight down, okay? The light spreads out. Sound spreads out. That's why I'm standing here speaking this way, but Margaret and Charlotte can hear me in each corner of the room because it spreads out, okay? Okay. reflection, sound waves may reflect when they hit a surface. A reflected sound wave is called an echo. You guys have probably done that. You go to the mountains and you holler off the cliff, you know, at one of the overlooked spots. Yeah, and it reflects off stuff and it comes back, and you can hear it. It sounds like someone, you know, you go hello, and it's hello, 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 because it's reflecting off of stuff. Okay. In general, the harder and smoother the surface, the stronger the reflection. When you clap your hands in the gym, you hear no echo because it's a hard surface. Wood, brick, and metal reflect sounds directly back at you. But if you don't always hear an echo in a room, but you don't always hear an echo in a room, in many rooms there is soft material that absorbs the sound. We've talked about that before.
Insulation.
Yeah. The old lunchroom, if you guys remember, had carpet framed out and hung on the wall. That was there to actually help absorb, Braxton, you're going to stop doing that, please. That it would absorb the sound. Your home, if you took all the furniture, the carpet up, and the drapes off the window, you'd be amazed at how different it sounded, because you wouldn't have anything to help absorb the sound. Okay?
Like when you move into a new house.
Yeah, when you move into a new house. Yeah, exactly. Yeah, exactly right. Okay? Diffraction. Have you ever wondered why you can hear your friends talking in a classroom before you walk through the doorway? You can hear them because sound waves do not always travel in a straight line. Okay? It actually can bend around openings. Okay? Sound waves can also diffract or bend around corners, and this is why you can hear someone talking in a hallway before you come around the corner. Okay? Interference. Sound waves may meet and interact with each other. You may recall this interaction is called interference. The interference that occurs when sound waves meet can be constructive or destructive. Constructive is when they meet and get bigger. Destructive is when they meet and kind of level each other out. Okay? The speed of sound, this is pretty good. Sound does not have this one set speed. Okay, kind of like light. I mean, light, we know light in a vacuum goes really, really fast, but if you've got something that can bounce off of, it doesn't go quite as fast. So sound, it happens because sound travels through air at the same speed. Okay, at room temperature, about 20 degrees Celsius, sound travels through air at about 343 meters per second. That's faster than most jet planes travel through the air. Okay, the speed of sound is not always 343 meters per second, though. Sound waves travel at different speeds in different mediums. And the speed of sound depends on the elasticity, density, and temperature of the medium the sound is traveling through. Okay? You see a chart here. In air, at 0 degrees Celsius, it goes about 331 meters per second. At 20 degrees Celsius, it's about 343 meters per second. That's in air. And remember, air is a gas. Okay? So it's spread out. Liquids, salt water, it will go 1,546 meters per second. When we get to marine biology, we'll talk about whales can communicate for thousands of miles away.
What do you mean by communicate?
They communicate. They talk to each other. They have a language that they use. Okay? They have a language that they use. Hey, they're smarter than most people I know. Okay? All right, in solids, at about 25 degrees Celsius, in glass, it will go 5,170 meters per second. Aluminum is about 5,000. Lead, it drops down to about 1,000, about 1,200 or so. Okay? So it depends. The elasticity, if you stretch a rubber band and then let it go, it returns to its original shape. However, if you stretch a molding clay and let it go, it doesn't bounce right back to where it was, right? Rubber bands are more elastic than molding clay. Okay? Elasticity is the ability of a material to bounce back after being disturbed. Okay? And it does the same thing with air, or with sound, excuse me. Okay? Density. The speed of sound also depends on the density of a medium. Okay, remember, density is how much matter or mass there is in a given amount of space or volume. The next time we're together, hopefully it'll be tomorrow, this ice storm will actually miss us. I've got some various little blocks. Some are wood, some are brass, some are aluminum, but they're all the exact same size. And we'll pass them around and we'll let you see just how the density will indeed change the weight of something. Okay? Sound will travel more slowly in a dense material such as lead or silver than in steel. Okay? Temperature in a given medium, sound travels more slowly at lower temperature than at higher temperatures. Okay? Why? Because at low temperature, the particles of the medium moves more slowly than the high temperatures. Chuck Yeager, on October the 14th, 1947, a guy named Chuck Yeager, he just passed away not too long ago. He was the first guy to break the sound barrier. He uses this knowledge to break the sound barrier. To fly faster than the speed of sound, Captain Yeager flew his plane to an altitude of more than 12,000 meters. The air temperature was negative 59 degrees Celsius. The speed of sound at this temperature is only about 293 meters per second. At 12,000 meters, Captain Yeager accelerated his plane to a record-breaking 312 meters per second, and by doing this, became the first person to break the sound barrier.
Wait, what does it sound like? What?
It's a boom. It's almost like a sonic boom.
It's like, okay, have you ever
You really
seen
do. And you'll see pictures. We'll look at some pictures when a plane is coming out of breaking it. It's surrounded by a big white cloud. It's like it's coming out of a time warp.
And I like when the plane passes by
Okay.
like a person.
All right. Hope you enjoyed this a little bit.